Hello AP Chemistry and welcome to more weak acids. I didn't put a title on this page, but this is just more weak acids. Okay. Really quickly, I want to go back and revisit this problem, right? So here you should have this, right? And I talked about how on the free response, work this out with the solve function on your calculator, right? On the multiple choice section, you would just assume that this minus x component is negligible, right? Not that x is negligible, yeah? So we're not saying that x is negligible, because if x is negligible, then this is negligible, which means it's a pH of 7, yes? That's not what we're saying. We're saying that the minus x is negligible, right? And that x is so small that compared to 0.01, it has no effect on this number in the grand scheme of things, okay? Now, I assume that we're all aware, right, that if we consider this part negligible, right, this math is really easy, right? 0.01 times this, turn this into scientific notation. What is this? Right, this is 10 to the negative 2. 10 to the negative 2 times this means 10 to the negative 7, right? So then I have x squared is equal to 1.5 times 10 to the negative 7, yes? And then that's what I would take the square root of, and I know that's going to be ballpark 10 to the negative 3.5. Yes? Make sense? All right. If need be, review your rules on, scientific notation and things. All right, so anyway, talking about weak acids and strong acids. So here we have two samples, right? This one is my strong acid. This one is my weak acid, right? So here I have 1 molar hydrochloric acid, which means that my hydronium ion concentration is 1 molar, right? Because it dissociates completely. Here I have 1 molar acetic acid, concentration of H+, not nearly 1 molar because it's a weak acid and does not dissociate completely. So as we watch, as we put in a piece of magnesium, right, reacts very vigorously, reacts, though not nearly as vigorously, right? So here your book talks about the larger bubbles, right? Because if we think about what a larger bubble is, right, larger bubble means it contains more gas, right? That's why the bubble's bigger. So anyway, that reacts vigorously, this reacts, right? And we'll see that shortly thereafter, this one is done, right? This one finishes much faster, but eventually this one does finish, right? Eventually both react completely, right? And that goes back to what basic principle? Ding, 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 Le Chat's principle, yes? In that, as this magnesium starts to react, right, thinking about, so we have magnesium, and what's it really reacting with? Right, it's really reacting with this to form Mg2 plus H2 gas, yes? Chloride ions being spectator ions, right? So this is the essential reaction that's occurring, right? So we know, though, as we consume this, right, as we consume that, and this, okay, this goes back to this reaction also, CH3COOH, right, CH3COO minus plus H plus, right? As we consume this, right, we actually force this reaction to go forward, right? So basically this is a coupled set of reactions happening in this one test tube, right? As we consume that 0.004 molar hydronium ion concentration, right, then this reaction pushes forward and makes more, right? And so it's basically a two-step circle that keeps happening simultaneously until all of this ends up over here because all of it ends up consumed, yes? Which is why when we talk about reactions with strong acids versus weak acids, right, they both react. They do the same thing, right? It's just not as vigorous and sometimes it takes longer, right? Assuming all other conditions are equal, yeah? All right, so this one says we found that the percent ionization, where it means exactly what it says, right? So it's the amount that ionizes over the amount that we started with, right? It's a piece over the whole, right? In 0.02 molar, blah, blah. Calculate the percentage of niacin molecules ionized in a solution that is 0.01 molar, right? So what's this really asking you to do? Right. If I want to know the percent ionized, I'm just asking you to calculate the concentration left over, yes? So we could find the H plus concentration and then subtract that over there so we could find how much is left over so we could then solve for my percent ionized, yes? Does that make sense? And this goes back to that graph in your textbook about how as the percent ionization or the percent ionization decreases as my concentration increases. So make sure you take a look at that graph. All right, polyprotic acids, right? This should not be hard, right? Poly means, right. Protic refers to protons, yes? Many proton acids. So here we have an example of citric acid, right? Wherein again, here we have that COOH group, except that it's actually, there are 3 of them in this one molecule, right? And if there are 3 of them, basically we have 3 acidic protons that are losable, right? Now, If we take a look at their relative Ka values, right? So citric acid, right? We see that as with all of these, right? The Kas, the successive Kas increase, right? Because at that point we're trying to remove a proton from a negatively charged species, which is a harder thing to do in terms of energetics, right? But here are things to look at. If something has successive Kas, right, that means that it has more than one proton to lose, which could mean that that math we did earlier gets more complicated, right? If we have to worry about this one comes off to some extent, and this one comes off to some extent, and this one comes off to some extent, what does that mean in terms of our pH, right? That could get really, really complicated. By the way, note that this, not one of our acidic H's, yes? Nor are these, yes? Right? It goes back to this carboxylic acid group in terms of organic compounds. All right. So here, the thing that we're looking for is as long as the successive Ka is at least 10 to the third different, it's negligible. Okay? If it's at least 10 to the third different, we can ignore it, right? So here, this is 5, this is 12, we can ignore Ka2, right? This is 7, this is 11, we can ignore Ka2. Here we can't, here we can't, here we could ignore Ka2, here we could ignore Ka2. Here, this one is, by large, we mean like really, really large, so we could ignore Ka2. And here we cannot, right? And that's assuming we're talking about having this species in solution, right? If we had this singly deprotonated form, right, then yes, this would become far more important because then we would be talking about this behaving as an acid. Yes? All right. Thank you for listening. Be good, and I will see you soon. Bye.